Good morning, everyone. We're going to continue along into our start of Chapter 9 here today. So we're going to go from Lewis structures in Chapter 8 and try to connect those to molecular shapes here in Chapter 9. So kind of saying something we've said a few times before, Lewis structures don't necessarily show us the actual shape of molecules. They're going to show us the bonding nature. They're going to show us, how many single versus double versus triple bonds does a molecule have, where are the lone pairs, or how many lone pairs are there. And then we can use these Lewis structures to help us determine shape, but we're going to have to think about how the lone pairs and the bonding pair electrons are going to try to repel each other and get as far away from each other as possible. So we see for atoms that have 2 or 3 atoms connected to them, we see a variety of different shapes. Like we can see linear versus bent when we have 2 atoms, like an AB2. So CO2 is linear. Now carbon dioxide, like if we look at it, has 2 double bonds, no lone pairs on carbon. The reason why this molecule takes a perfectly 180-degree bond angle is because it has the 2 bonds want to get as far away from each other as possible, and for them, that would be 180 degrees. Now, the difference between CO2 and SO2, they look very similar in terms of formula, just changing a carbon to sulfur, but the difference is we add 2 more electrons to the mix. So we go from having 16 total electrons for CO2 to 18 total for SO2. The difference is SO2 has a lone pair of electrons on the central atom. So when we look at a Lewis structure, like let's say we write the Lewis structure for SO2, you can write it one of 2 ways. Let's actually do the way that we don't necessarily always like the best, where we do the double bonds. So let's sketch this Lewis structure real quick, because that has 18 total electrons. Sulfur has a neutral formal charge. Oxygen has a neutral formal charge. What you can see here, the difference between this and carbon dioxide are those 2 electrons there. Those 2 electrons repel the bonds, so the bond angles can't go 180 degrees here because they have that lone pair of electrons. It's like, hey, get out of my way. So the electron pairs here force the bonds into a different geometry. So the way we can sort of classify a geometry is that all of the sort of things around a central atom, we sometimes call these domains, but if you take the 1 non-bonding domain and then the 2 bonding domains, I have 1, 2, 3 total domains. Let me rewrite domains. So what a domain is it's either a bond to another atom, and that bond could be single or it could be double. It doesn't matter what the type of bond is, but a bond to a given atom is one domain. So we have 2 bonds, so we have 2 bonding domains. We have 1 non-bonding domain. So we have 2 bonding domains for SO2, and we have 1 non-bonding domain. So a non-bonding domain is just like that pair of electrons. And so when we have 3 total domains, they're going to take the shape that 3 shapes can take. That's that trigonal planar geometry. So we saw last time that things that have 3 domains take the shape of a trigonal plane. So the geometry here is about 120 degrees for all of these components, for the lone pair to the bond pairs to each other. So SO2, that bond angle is closer to 120. Now, in a little bit, we'll think about the difference between lone pair and bond pair repulsions, but let's come to the actual bond angles and some effects that the lone pairs have on the bond pairs a little bit later. For SO3, now it doesn't really matter which Lewis structure. If I'm thinking of a Lewis structure where maybe I wrote something that looks like this as a Lewis structure for SO3, where SO3 only has 24 total electrons, and so maybe I have 1 double bond, 2 singles. I could have 3 doubles. Both of those are acceptable. This might be the better Lewis structure of the 3 to sketch. It doesn't quite matter because, 1, there is resonance going on, so all those bonds are identical. So if you remember, the effect of resonance would be that I could sketch equivalent yet different Lewis structures. So I really have 3 equivalent bonds that have an equal bond angle. I thought it was a ghost at first. So all those bonds are identical, but even if we think they're identical or we don't think they're identical, there's still 3 total domains there. And so I still have 3 domains, no non-bonding domains. So So the geometry that molecule takes is that perfect trigonal planar geometry. So now when I have 3 atoms on a central atom, it could take this shape. This is the shape that's adopted by molecules that have no lone pairs of electrons. But then we could have something like NF3, which is also AB3. If you look at the formula, you may think, well, if SO3 is trigonal planar, would NF3 be trigonal planar too? Not necessarily, and it doesn't because we have that lone pair on nitrogen. So if we try to sketch the Lewis structure of NF3, we'd have something that looks like this for the central nitrogen, lone pairs on the fluorines. That's 24 electrons, but NF3 has 26 electrons. The 2 left over onto nitrogen. So nitrogen has a lone pair. So the lone pair and the bond pair repel each other. So the domain geometry that 4 total domains can take is tetrahedral. So with tetrahedral domain geometry, but where I have an electron pair on one of those spots, the AB3 NF3 now takes a different shape. When I name the molecule here as trigonal pyramidal, that's the name of the atom. So I'm trying to name the shape of just the atoms, trying to say, well, what's the shape that the atoms take? And the shape isn't tetrahedral. The shape of trigonal pyramidal comes from the idea that the domains take a tetrahedral geometry, but the shape we try to name just the shape of the actual atoms. So the molecular geometry name is where are the atoms? Now you might wonder if the shape of the molecule is really coming from being tetrahedral based for all of its electron domains, why do we give kind of, if you will, 2 names? We will name an electron domain geometry for a molecule and its molecular geometry. Why do we do this? I don't know. Maybe it's because it's in the book is one thing, but the real reason I think is because when you go to experiments, and an underlying part of chapter 9, I think that we get a little backwards the way we tend to teach this topic, is that the way you would really try to learn structure is you would go to nature, try to determine what the structure is. The way you can determine the structure of a real molecule in nature would be to do like an X-ray crystal structure analysis, or use X-rays that atoms will show up on an X-ray crystallography structure where electrons won't. So you can see where the atoms lie, and that's your geometry. You can't really exactly see where the lone pair of electrons are, but you can interpret it or infer or understand the shape of the molecule as being dependent on that electron pair being where you think it is on something like NF3. So while we can't visualize this electron pair here, we can understand nitrogen has to have that lone pair, and that must be why it takes the geometry it does. So the way you would determine geometry, like if we could teach this class over a longer period of time, we would probably teach you what that X-ray technique is. We'd probably teach you what the structures look like. We'd probably then try to figure out why the structures are the way they are, and then generalize it. Imagine somebody did that before. We've generalized the structure, we've generalized the rules down to what really determines a given molecule's geometry is how many bonding domains does it have, how many non-bonding domains does it have, what's the shape that would take, and then from that shape, we can predict the shape of the molecule. So you can kind of see that if you could predict the structure based off of analogies that you've seen in reality, you can then come up with a set of rules that we're trying to teach you that can then allow you to predict the shape. So we're trying to predict shapes that give us the real shapes of the molecules that we could then go verify with experimental analysis. So again, with 3 atoms attached to a central atom, you may say, are there other shapes we get? There is another shape. We get a T-shaped molecular geometry. We get this for a molecule like ClF3. Meaning if you go into nature and look for a molecule, look for the structure of ClF3, it turns out to have a geometry where these bond angles here are closer to 90 degrees, not closer to 120 like SO3. The bond angles in NF3 are closer to 109.5 degrees. Now we're closer to 90 degrees in ClF3. Why is this? Well, let's think about the electron pairs on chlorine. So ClF3 would have a total of 28 electrons. 7 times 4. And so if we have electron pairs around the fluorines, that's 8 for each of the fluorine. That's 24 electrons. The 4 left over, where do they go? They are placed onto the chlorine atom. So chlorine has two bonding domains for non-bonding pairs, plus the 3 bonding domains. So for ClF3, I have 5 total domains. For NF3, I had 4 total domains. For SO3, I had 3 total domains. So what's changing for these different molecules is the total number of domains is changing. So we're going from having 3 to 4 to 5 now total domains. Now where these electron pairs would be, if you imagine that the molecule has its bonds in the plane of your iPad or whatever screen you're writing on, these electron pairs would actually be sticking straight out of the page. So in terms of ClF3, we'd have an electron pair kind of going into the screen and coming out of the screen. And so these electron pairs would be kind of in this shape of a trigonal pyramid. There's a few different ways you could try to sketch this. Like if you imagine trying to flip this ClF3 this way, you can maybe picture a lone pair coming out this way and going into the screen this way. But it's just taking a 3-dimensional shape of a trigonal bipyramid. So if you imagine having something trigonal like SO3, and then having a lone pair sticking straight out and straight into the page. So imagine a structure like this, and you can almost picture your pencil or whatever on your screen sticking straight up. That's where the lone pair would be on that type of a shape, or going into the shape if we had 2 more electron pairs. Okay, so the electron pairs just take the spot on, if you will, the equator of the molecule. We'll talk about the different positions of a trigonal bipyramid in a minute, but they take the 2 spots on the equator of the molecule to give us the shape of the T-shaped ClF3. So the ClF3 on this side of the molecule here. Now, what determines the shape of a molecule is kind of the minimization, if you will, of the repulsions of these electron pairs. The bond pairs repel each other, the non-bonding domains repel each other. So the molecule is just trying to take the shape that minimizes all those repulsions and gives it the most stable or the lowest possible energy. And so nature does that. So if you go to nature, try to determine shape, and then try to generalize the shapes, those are the shapes that we're showing you. So somebody before us has come in, determined these shapes. We're trying to generalize those to understand and predict shapes of other molecules. So when we see molecules that have the same number of domains as these molecules, are going to adopt the same basic shapes. So the basic idea here is if we can write a Lewis structure, and even to kind of not necessarily go back to the last slide, but if you're looking at some of those Lewis structures we could sketch in the last slide, the Lewis structure is not showing you the geometry. We have to interpret the geometry from the repulsions all of those bonding and non-bonding domains can have with each other. So the basic process would be, try to write the best Lewis structure we can, account for all the valence electrons, because that allows us to determine the proper number of electrons on a central atom. Then we can determine the electron domain geometry based on the total number of bonding and non-bonding domains. So if we're doing this for like NH3, where we have 5 plus 3, that's 8 total electrons. So we have 3 single bonds to hydrogen, and then the remaining 2 electrons onto nitrogen. So I have a total for nitrogen of 4 total domains. So I have domain 1, 2, 3, and then 4. And so what I have to do is I have to fit that into the domain geometry for 4 total domains. So 2 domains linear, 3 domains trigonal planar, 4 domains tetrahedral. And so the shape of NH3 is going to go into the electron domain geometry of tetrahedral. So we can determine and arrange the sort of the electron domain geometry based on the total bonding and non-bonding domains. So 4, that goes tetrahedral. TD is what we symbolize tetrahedral with. And then the actual geometry of just the atoms. So if you imagine trying to do an experiment where you can see the atoms, you're going to see a geometry reflective of a molecule that's tetrahedral electron domain, but the 4 atoms taking the shape of this. And so the shapes, if you can picture the shape, you're just trying to name what that shape could be called. And so like we wouldn't call it trigonal planar. Like when I say planar, the whole molecule needs to be in one plane. That molecule's not planar, right? The nitrogen's sitting above the plane of the hydrogens, and it's creating a pyramid. And so this looks like a trigonal. So I get a trigonal from the hydrogens and then pyramid. So that's what we call this, a trigonal pyramidal molecular geometry. If you can picture, if you can sketch, if you can try to consider the shape of the molecular geometry is just the name that shape is showing us. It's going to be hard to, I think, just memorize like the domain count for bonding versus non-bonding in terms of a shape without just trying to picture these things. If you can picture it, it's so much easier. So the idea here for CH4 has all 4 bonding domains, 0 non-bonding domains, so that's just tetrahedral for both. So if you have a molecule that has no non-bonding domains, all bonding domains, then the electron domain geometry name is the same name as the molecular geometry name. So CH4 is tetrahedral electron domain and molecular geometry. Now ammonia and water, so water has 2 lone pairs on oxygen, 2 bonds to hydrogen. Both these molecules, NH3 and water, are tetrahedral electron domain. So they each have 4 total domains, so they're still fitting the basic shape of the tetrahedron, but just where we lose one of the spots in the tetrahedron to a lone pair. And so we have a lone pair for nitrogen, so trigonal pyramidal for the shape of the atoms. And then again, if you, like, one of the basic ideas, whenever you have 3 total atoms in a molecule, it's either linear or bent. Those are the only names that can apply. It's either going to be perfectly 180 or it's not 180, and we call it bent. And so water, of course, has to be bent because that bond angle is nowhere near 180. So the bond angle in water should be close to 109.5 degrees because that's the bond angle of a perfect tetrahedron. Now, I think the next slide, or the slide after, gets into the relative repulsions of lone pairs versus bond pairs, but you can probably imagine, like, which electron pairs are closer to the nucleus, the lone pairs or the bond pair? Probably the lone pairs, meaning these pairs of electrons are probably closer to the nucleus because there's no nuclei stretching them out. And so remember, these dots are negative particles, and the negative particles are repelling the negative particles in the bonding domains. So if you take 2 pairs of electrons, put them closer to the nucleus, how do you think the bond pairs respond? They're repelled and going to decrease in bond angle. So the bond angle in water is not quite 109.5. They're going to be compressed to be a little shorter than 109.5. I think it's on the next slide. It's about 105 degrees. NH3, it's not as pronounced because there's only 1 pair of electrons. So this turns out to be about 107 degrees. So if you can determine, that's an experimentally determinable value. If you look at the bond angles, the idea would be, okay, we're using the idea of the valence shell electron pair repulsion. So the valence shell atoms are repelling each other. And then the closer they are to the atom, the lone pairs are closer to the atom, so they exert a greater repulsion on the bonding pair atoms, pushing them closer together, showing us that if you have 2, it's even more pronounced than just having 1. So ammonia's bond angle is about 107 degrees. So that's on this slide here. So it's just kind of thinking what having 2 nuclei do is they're going to take those electrons, spread them out. We write them either spin up, spin down. But the key is that these are 2 negative particles. If you put those negative particles closer to the nucleus, then they're going to exhibit a greater repulsion on the bonding pair domains. So non-bonding pairs are physically larger. You can also think the shell size kind of increases more this way instead of being this way when you pair up an atom with another atom. So having an actual bond elongates an electron pair, makes it more narrow. Having a lone pair makes it broader and closer to the nucleus. And so this is just showing you the comparison between perfect tetrahedral to less tetrahedral and a little bit less tetrahedral for water. Now, predicting bond angles helps us understand, if you get the picture of what the geometry is, where the non-bonding pairs are, and the idea of the relative repulsions, that the non-bonding pairs have greater repulsions with the bond pairs in a given atom, or in a given molecule. Now let's think about the bond angles with double versus single bonds, because we see an interesting trend here. You can see it with the molecule COCl2, which is the molecule phosgene, actually a nerve agent molecule. But so double bonds are going to repel single bonds to a greater extent. Why? I have 4 electrons here. I only have 2 electrons here. So having 4 electrons will exert a greater repulsion on the 2 electrons. So COCl2, it's trigonal planar molecular geometry. Trigonal planar should be closer to 120 if it were perfect. Perfect trigonal planar would have been 120 degrees all the way around. The molecule is still planar. It's not flipping in and out of the plane. The molecule is still perfectly planar. What's changing is the bonds of the chlorine are getting closer together because their repulsions are less. The double bond repels those single bonds more, pushing those single bonds closer together. So you can see the single bond's a little less than 120. The double bond's a little greater than 120. So you can see here that double and triple bonds have greater repulsions on the single bonds. Now, if we think of a triple bonded molecule real quick, like HCN, this bond angle is still perfectly 180 degrees because there's no other way, like if it pushes it one way, it will just push it back the other. So having two domains will always be exactly 180. So perfectly 180 for HCN, but if we have a double bond, single bond repulsion, we're going to kick that into the double bond repelling those single bonds to a greater extent. Now what about SO3? So this is SO3 here. We saw earlier, it's trigonal planar geometry. Now we have to interpret resonance. When I interpret resonance, when I think of having these three equivalent Lewis structures I could write, the real molecule is the average of those three. So the real molecule looks like this. It looks like the composite of that double bond being shared across the two atoms at all times. What effect do you think that has on the bond angles? Do you think it makes one of the oxygens get closer together in one of the bonds? Or do you think it remains being perfectly 120 all the way around? It remains being perfectly 120. So we have to interpret and think about resonance, or sort of think about how COCl2 doesn't have resonance going on. There's no way I can sketch equivalent in different Lewis structures, so I don't have this effect on the molecule COCl2, so it responds by having different bond angles, but I can sketch those two other Lewis structures that are equivalent to the one we wrote here for SO3. The real molecule is the average or the composite, so the real molecule looks more like this, where all those bonds are identical, hence all these angles have to still be perfectly 120. So we got to be careful of thinking about localized versus delocalized bonding. So I have a localized double bond in COCl2. I have a delocalized bond in SO3. So the delocalization kind of removes the effect of that double bond, single bond repulsions because I really don't have a double bond. Let's think about electronegativity. So this is back in chapter 8. We were thinking of things like HF, having a dipole moment or being polarized. So we had these partial positive negative charges. So for diatomic molecules, they're polar when their atoms have a different electronegativity. So the greater the difference of electronegativity, the more polar the bond. If we pair fluorine up with itself, of course, a really easy example of a nonpolar bond is just a molecule that's diatomic with the exact same atom in both spots. So like F2 is perfectly nonpolar, despite having two really electronegative atoms, because both nuclei have the same pole, and the electrons, of course, both atoms have zero formal charges and truly zero real charges in the molecule. So we can have a nonpolar bond, we have the exact same atom paired up with itself, and then we can have a polarized bond in the case of HF. Now, in the case of chapter 9, we want to get into what about larger molecules? What about molecules that have 3 or more atoms? Can we predict if they're polar? So how do we determine if a molecule like water versus CO2 is polar? Because it turns out, let me just start with a blank slide rule here to compare two molecules of water, where water, of course, has that bent bond, has that bent molecular geometry, not perfectly 180. Carbon dioxide, perfectly 180. And so if we're looking at carbon dioxide, perfectly linear, 180-degree bond angle. Now, these two molecules I think are really important to compare because they have a really big difference in that one of them's polar, one of them's nonpolar, but the nonpolar one still has polar bonds. If I'm looking at carbon dioxide, carbon and oxygen have a pretty big difference of electronegativity. Oxygen's picking up a negative charge, carbon picks up a positive charge, and it's going to be fairly big partial positive and negative charges. But what happens if we think of polarity as being like a vector? If we have a vector pointing towards oxygen, what happens to the other oxygen? It has a vector of the exact same quantity pointing the exact opposite direction. Mathematically, what happens to those two vectors? They cancel each other out. If we have exactly the same charge opposing each other on all sides of this molecule, those dipoles just kind of disappear. The dipole moment of the molecule is 0. The molecule is perfectly nonpolar, despite having polar bonds. So even though the molecule is polarized in a sense that carbon and oxygen have a difference of electronegativity, even though we can see and predict and sort of understand that the molecule is going to have partial negative charges on the O, partial negative charge on the other O, partial positive on carbon, that the overall molecule ends up being nonpolar. And this has major consequences. If you compare that to water, where water now has the dipoles pointing in towards oxygen, but now angling in this way, and now, I mean, this is math that I don't know if it's worth talking about. If you have two dipoles pointing this way, the overall average is going to point this way. So the average dipole is going to point this way, right? In towards the oxygen. We don't need to do the mathematics to know that, right? That there's going to be a big dipole for the molecule pointing towards oxygen, meaning I get this negative end here, and I get the positive end here. The difference here is if I put two water molecules adjacent, do they have a special built-in attraction for themselves? And they do, because the dipoles can align. So the two water molecules would align by their dipole moments. We'd have the negative of the O being attracted to the positive on the H, and we'd replicate this for the molecule ad nauseum. We'd have a very strong force of attraction. I don't get that for CO2, even though we have the polarization, even though we have the polarized charge centers. I just basically have kind of balls of negative charge here. If I put two CO2 molecules next to each other, there's no inherently strong force of attraction between those molecules because of their polarized bond. I need that dipole. We needed that dipole to align, to orient, to allow the molecule to experience the charge. Another thought would be, if I put like a negative charge somewhere and said, what do the molecules do if I put a negative charge nearby? The water is going to, the hydrogens are going to go towards that charge and be attracted to the charge. If I flip this charge to positive now, make it a positive charge, the molecule is going to flip, and the oxygen is going to want to be near that charge. What if I put a negative charge near CO2? What does it do? The oxygens run away from it. The carbon might want to run towards it, but the other oxygen prevents it. So the negative charge here and here would be repelled. The molecule is not attracted in towards that charge. If I flip this charge here, you might think there's enough negative charge to head towards the direction, but the two negative charges would fight over it. And the molecule would just start spinning or fly away due to repulsions. So we don't get that attractive force where CO2 would head towards that charge. So there are a few different ways you can think of the manifestation that being nonpolar, the effect that leads CO2 to have a different behavior than water relative to the attraction with itself, or to the response of adding a charge nearby. Now, the effect that this has on the molecule is it makes the melting point and the boiling point of water be a lot higher. So the melting point of water is a lot higher than it is for CO2. So CO2 is a solid to, what is it, minus 78 degrees C, I think, is so at minus 78 degrees C, CO2 actually transitions to a gas. So dry ice sublimes at minus 78 degrees C, skips the liquid phase altogether. We'll talk about that a little bit more in chapter 11. But CO2 is a gas at room temperature. Water is a liquid at room temperature. If it weren't for water being polar, it never would have been a liquid at room temperature. So a lot of the properties of water have everything to do with those built-in charges, and it also has a lot to do with hydrogen being small. So we're going to talk about, you've probably heard about hydrogen bonding forces of attraction, but putting a relatively large positive charge on a small atom allows it to have a strong attractive force. So those are important properties for water that CO2 doesn't have. So two important molecules, two distinct differences. So one's nonpolar, one's polar. So water is a polar molecule, but they both have polar bonds. Let me see. So when we think about polarity between bonds versus molecules, bonds are polar. So we look at bond polarity. It's just a simple difference of electronegativity. So bond polarity is a measure of how equally or unequally the electrons in the covalent bond are shared. So the greater the difference of electronegativity between the two atoms, so the further away the atoms are on the periodic table, the more polar the bond is. This is from chapter 8. And so in nonpolar covalent bonds, the electrons are shared equally, so that's like F2. And then in a polar covalent bonds, one of the atoms attracts the electrons to itself with a greater force, so that's something like HF. And we get the partial negative, the partial positive. But now in a molecule, so compare the difference between a single bond between two atoms and a molecule is polar when it contains polar bonds and the bonds are situated in such a way that the molecule can become polarized. So we have to have the molecule situated in a way that we can get a positive end and a negative end. I need the ends of the molecule to differ in charge. There's a lot of examples that we'll look at in this chapter, but just look at a couple right off the bat would be to compare maybe like SO2, some Lewis structures we've already been sketching and thinking of, versus like BF3. So for BF3, central boron, trigonal planar, the bond's really polarized. We talked a lot about this. The bond's certainly polarized, but notice how we have these perfect 120-degree bond angles, and I have the ends of the molecule that are exactly the same charge as each other. So I have the exact same negative charge on one F as the other F as the other F. This molecule, those dipoles, the individual bond dipoles would all cancel out. So this molecule here, BF3, is nonpolar. Like one thing that you could probably start to picture, and we'll show examples as we continue. There's so many examples of polarity that we can sketch. But if you can have linear trigonal planar geometry or tetrahedral geometry, even the bigger trigonal bipyramidal or octahedral geometries, if you can picture all of those electron domain geometries where you have all the domains are bonding, and then the exact same atom is in all the spots, then we're going to have a nonpolar molecule. So if we do this like right off the bat with, say, PF5. So if PF5 has 40 total electrons, 5 plus 35. And so for 40 electrons, we just have that trigonal bipyramid geometry. And all those dipoles are going to magically cancel each other out. This molecule ends up being perfectly nonpolar. And it's not because the bond's not polar, it's just because of the situation of the bonds. That all the bond dipoles are going to perfectly cancel. The two phosphoruses on the axis will cancel, the ones on the equator will cancel. We end up with a perfectly nonpolar molecule. Now what about SO2? Let's do SO2 over here. That was the one that had 18 electrons where we had the lone pair on sulfur, and then we had something that looks like this. So we have that bent bond for SO2. Now, oxygen's more electronegative. We have electron density pulling towards the oxygen. Oxygens are partial negative charged. Depending on the Lewis structure you write, they may already have zero formal charges. If we're picturing the Lewis structure, that one of them look like this, the other one's single with lone pairs around, then we're sharing a -1 charge across the two atoms. So oxygen certainly has a negative charge as the consequence. Whether you're picturing it through the resonance effect, or if you just want to sketch it with two double bonds with the other Lewis structure that's acceptable, where the formal charge is 0, but oxygen is more electronegative. But the key is the bond is bent. It's this bent bond here that allows this end of the molecule to be negative. Sulfur has a partial positive charge, so the positive charge on sulfur is the positive end of the molecule. Now, what I need for a molecule to be nonpolar would be something like SO3. I would need something where I oppose those two charges with the exact same charge up here. So SO2 would be a polar molecule because we're not canceling out the charge exactly on every end of the molecule. But then if I go to SO3, let's even sketch that exact same Lewis structure as earlier. We might have to think about resonance. But when we think about resonance, I have the exact same charge on every end of the molecule. If I think of putting the electrons here, or putting electrons here and averaging those out, I'm averaging out to put -2/3 of a charge onto each of those O's. So if I imagine this structure here, where I'm taking that extra double bond, spreading it across those three other bonds simultaneously, remember how we were calculating that these bonds would be of an order of about 4/3? Because I'm taking 1, 2, 3, 4 bonding pairs spread across the three bonds. Well, think about the charge on the O's. The charge on the O's are either minus, minus, or 0. So I'm taking the -2 charge and spreading it out across the two O's. What I'm trying to show, trying to make sure we're thinking this, is that those oxygens have the exact same charge. It's those O's having the exact same charge and the molecule not having anything geometrically that allows one side to be positive and the other to be negative. I need there to be like a plus end and a minus end, not just like a big minus ball on the outside of the molecule. And so this molecule here, SO3, perfectly nonpolar. So what we mean by nonpolar is if you look up the dipole moment, it's exactly 0. If you look up SO2's dipole moment, you could probably Google it, but it's not going to be 0. So SO2 will have a dipole moment, will be polar. BF3 perfectly 0, PF5 perfectly 0. So this is showing us kind of the electrostatic charge potential, if you will, kind of showing the difference between CO2. We get negative charge here. And again, if you imagine putting like a positive charge here, you might think that this end of the molecule would fly towards the charge, but then the other end will fight for it too, and the molecule will just start to spin. So the molecule is not going to fly towards the charge. If I put a positive charge for water, the negative end is going to fly towards it, and it's going to be stuck there. It's going to flip over, go towards the charge, and be very happy. CO2 is not going to know what to do with the charge. So that's the difference between being nonpolar and polar. The other difference is just the two CO2 molecules don't have that same built-in attraction for themselves. And so when I'm trying to, when we get to chapter 11 later, we'll predict, stronger forces of attraction, things that likely have a higher versus lower melting point relative to each other, or higher or lower boiling point relative to each other. So there's a really good reason why we want to determine whether something's nonpolar versus polar. I think sometimes in chapter 9 you may feel like it's just a weird term you give a molecule that doesn't mean anything. It has a tremendous amount of meaning. Polar molecules have much stronger forces of attraction with each other than nonpolar molecules do. And there's a lot of properties that change as a function of whether a molecule is nonpolar versus polar. So water's polar, CO2 is nonpolar. Okay, so we've already done some of these, like HCN. Maybe we haven't done it within the context of being given the formula. Like, how can I take HCN and sketch a formula? I have kind of like there's probably 3 ways to sketch Lewis structures. One way is just counting up electrons. So like the easy way, or maybe this is the hard way, if you have to do it this way, just add up the electrons. We get 10 total, just from using the periodic table. And then we connect the atoms to the non-central, give the non-central an octet, and then look at the formal charge on the central atom, think about multiple bonding to satisfy its octet rule. And so then we satisfy carbon's octet with a triple bond to fill it with an octet, give it 8 total electrons, minimize its formal charge down to 0 from what was +2. And then nitrogen was -2, now nitrogen is 0. So we're minimizing the magnitudes of formal charge by making double bonds. Okay, so that's one way we can come up with a Lewis structure. Another way could be to think of dot structures. So to connect to a bond here, and then nitrogen like this. So we could take and kind of connect dot structures. Sometimes it's helpful for coming up with Lewis structures. I've mentioned sometimes that this sometimes just doesn't work for things that are anions or things that are bigger. So this approach maybe isn't always great. But for things that contain like HCN, like getting into like organic molecules, you're going to see in this chapter, we'll start to sketch Lewis structures for just almost like a random formula. Like we'll say like CH2, CH, CH, something like that. You can start to connect the atoms and consider that carbon is almost always going to form a stable molecule with 4 bonds, no non-bonding pairs. Nitrogen forms very commonly compounds with a lone pair and 3 bonding domains. Oxygen, like water, 2 bonding domains, 2 lone pairs. And so when I start to see things like, CH2O, and I know I need to connect the hydrogens to carbon and the oxygen, it just kind of goes that, well, why don't I go double for the carbon, 2 lone pairs on oxygen, no lone pairs on carbon. Hydrogen likes to form 1 bond. So, we can sketch a lot of Lewis structures just by the kind of properties of a given atom. So you'll see us kind of with a third approach here in chapter 9, of as we get into some big organic molecules, just kind of using some basic ideas of keeping the formal charge at 0 through satisfying the octet rule. Ozone, O3, has that central oxygen, 18 electrons. It's like whenever I have one where I'm like, I don't know what to do with O3, I count the electrons. So if I'm not sure what to do, just count them up, distribute 16 of them this way, and then put the lone pair on oxygen, because that's our leftover 2 electrons. And then maybe make a double bond, and then it can resonate over to here. But the key for the electron domain geometry name and the molecular geometry name is just getting the number of non-bonding pairs right and the number of bonding domains correct. So for O3, I have 1, 2, 3 domains. Now, it's not really a double and a single, right? It's really the resonance effect of a 1.5 bond here and a 1.5 bond here. But for chapter 9, it doesn't matter. It's just 3 total domains either way. So I have 3 total domains. So for O3, that's trigonal planar, electron domain, and then it's going to be bent molecular geometry. Because the electron pair has to force it into bent.
Do you not count the lone pairs that aren't on the central atoms? You only count the ones that are on the central atom?
Towards the total domain, or
Yes.
yeah, so I would have one domain here, and this would be 2, and this would be 3 total. So 3 total domains. 3 total domains is why it goes trigonal planar. And so I haven't sketched the real shape. So, okay, so like maybe if you were looking at it thinking I was trying to sketch it linear, I just need to re-sketch the shape. When I do a Lewis structure, sometimes I'm not necessarily knowing what the shape's going to end up as. So for O3, it's going to look more like this, lone pair, the bond being shared. So it's going to have this geometry here. This bond angle should be a little less than 120 because of the lone pair bond pair repulsions pushing that bonding pair a little bit past 120. It also said to estimate the polarity and give some other names. So like HCN, we forgot to name that as linear, but we had named that previously. Now for O3 or HCN, let's do HCN first. Do you think that's polar or non-polar? So what do you think about HCN, polar or non-polar? Nitrogen is certainly more electronegative than carbon. That bond's definitely going to be polar. NO and F are the 3 most electronegative atoms. You pair them up with anything other than themselves, they have to be polar. And by themselves, I mean N2 versus O2 versus F2, not NF bond. The NF bond's certainly polar, the OF bond's polar, the ON bond is polar. It's just a atom with itself is always going to be nonpolar, of course. So this molecule doesn't have the exact same charge. What I need is a negative charge on H that's the exact same charge as the negative charge on N. And that's never going to be the case because there's a different electronegativity. And so this molecule here will be perfectly polar, meaning it has a negative N and it has an N that just doesn't have that exact same charge. Ozone's a really interesting molecule. Ozone's interesting in the regard that if you look at the Lewis structure here, you get a negative charge versus 0, and then the central O has a positive formal charge. So I have a positive charge here, and I have negative half charges in terms of the formal charges on the 2 O's. Now, so the structure kind of slants oxygen towards having different charges, but they are the same nuclei, fighting for the same bonding pairs of electrons. So the positive O is going to pull the bonding pair back towards itself, but ozone turns out to have a dipole moment. So you can see the difference in charges does lead it to be a polar molecule. I think that's a really tricky question because if you look at O3, you'd say, well, it has the same nuclei. How can it possibly be polarized? But it's just a consequence of the Lewis structure where we have a positive end and a negative end. And so that's the definition of being polar. So we have a negative dipole. The dipole vector, if you will, is always pointing towards the net negative charge. So the 2 dipoles, so individual bond dipoles, you can think of those towards the 2 O's with the negative charge, and then the overall dipole moment splitting the molecule. What about OF2? Now, at some point, you may be sitting there saying, I know the Lewis structure without sketching it, but if you're not sure, just go 6 plus 2 times 7, 20 electrons, central oxygen, 2 fluorines attached with lone pairs, and then count electrons at 16, 8 per each fluorine. That's 4 electrons left over onto the central atom. So in terms of geometry names, this is tetrahedral electron domain, and then bent geometry. So this would be a bent molecular geometry. This angle here is certainly not 180. It's going to be closer to 109.5 and, of course, a little less than 109.5 degrees because of the lone pair bond pair repulsions pushing the bond pair electrons closer together. So those repulsions are pushing our OF bonds to be less than 109.5 degrees. If you notice on my paper, it looks like 90 degrees. Like the way I sketched the bonds was that they were closer to 90. Remember, like when I sketched the Lewis structure, I wasn't thinking about the geometry. I'm interpreting the shape from the electron domain geometry. Like for example, if I write CH4 this way, you'll see me do this a lot where I'll do this, that this bond angle here is 109.5 degrees. How's that possible? Well, because that's not the geometry. Like I can sketch a Lewis structure. I'm just going to sketch it almost always 2-dimensionally because it's easier that way. It's a lot easier to sketch a flat Lewis structure and then look at it and be like, okay, That's going to be tetrahedral because it has 4 domains. Tetrahedral is 109.5 degree bond angles. If it's helpful, maybe we resketch it. So if I have to, I can resketch it. That's how you can picture it's really 109.5 degrees. So sometimes we're interpreting shape from a flat Lewis structure, and it becomes a question of, do we resketch it with the shape, or do we just try to picture it without resketching it? Let's talk about the difference between, so for trigonal bipyramidal shown here, for like something like PF5, let's say, that we have, if you notice, like these fluorines are inherently different than these fluorines. Like there's a difference between whether the fluorines are like 90 degrees relative to the other fluorines or 120 relative to the other fluorines. That these are like equatorial, they're on the equator of the molecule, and then these are like axial, meaning they're on the axis of the molecule. The other shapes didn't have this issue. Like if you go to linear geometry CO2, the 2 oxygens are identical. If you look at BF3, trigonal planar, the fluorines are in identical positions. If you look at CF4 or CH4, the hydrogens are in identical positions. There's no difference between the position those atoms are in. But as soon as you get to PF5, and only within trigonal bipyramidal, you have this issue of having axial versus equatorial. It just means that there's different positions on the structure. What this then means is if we're going to replace one of these spots with a lone pair, that we have to think a little bit, or the molecule had to think a little bit about which one's going to be lower in energy. So if I'm going to replace a spot with an electron pair, it turns out I take an equator position, not the axial position. So if I'm going to lose a spot to a lone pair and replace it with a lone pair, I choose the equatorial position. And if I choose a second pair, if I have to make a geometry for trigonal bipyramidal domain with 2 lone pairs, I replace another equatorial position. And then lastly, if I have to have 3 total non-bonding domains, so if I have to have trigonal bipyramidal with 3 non-bonding domains plus 2 bonding domains, that's 5 total, then I choose another equatorial position. So I'm always like replacing lone pairs on the equator. Now the reason why is because that's what nature did. That's what the molecules chose and must have been the structure that minimized the repulsions the best. Because that's what molecules are going to choose. They're going to say, is it less repulsive for the lone pairs to put them like 90 degrees, like on the axial position, on the equator position? It turns out for trigonal bipyramidal, it's on the equator position. Now, when you picture something like SF6, you just don't have this problem anymore. So when you picture something like SF6, where the molecule is octahedral, and now if you remember, octahedral is not named for the number of fluorines, because there's 6 fluorines, that would be hexahedral. It's named for the 1, 2, 3, 4-sided pyramid, 1, 2, 3, 4-sided pyramid above and below. So we were talking about this last time, and I think it was the end of class, and I'm sure eyes were glossing over at that point. Maybe they are now again. But I think you can clearly see the octahedral shape is named for this shape you get by the pyramid shape you're connecting with the structure. But now, if you notice here, all the atoms are on the equator. So you don't have this issue with octahedral. There's only one position again for an octahedral geometry. So let's kind of go through the permutations of the structures you get when you have 5 total domains. If all of them are bonding, then that's really easy. That's just trigonal bipyramidal shape. So that's like PF5, PCl5. Then if you have something like SF4, where you have a lone pair, 4 fluorines, lone pairs on each of the F. SF4 is a total of 6 plus 28, that's 34 electrons. So you get that lone pair on sulfur. Just making sure you see the Lewis structure comes up with 1 non-bonding pair of electrons and then the 1, 2, 3, 4 bonding domains. And so the shape here, we replace a pair of electrons on that equator of the molecule like we were talking about earlier, and then we end up with a shape that we call seesaw. Now, if you imagine this shape here, why do we call it seesaw? It literally looks like a teeter-totter. Like if you picture the fluorine to sulfur to fluorine, fluorine's coming out. If you sketch it this way here, do you see how the molecular geometry name looks like an old playground piece of equipment? So literally, we're just naming that shape, and that becomes the name seesaw molecular geometry. So this is why I said, if you just try to memorize 4 bonding domains, 1 non-bonding domain is seesaw, if you're just trying to memorize that and you forget, is that one the seesaw? Or is it seesaw if we have 3 bonding, 2 non-bonding? you just look at the molecule, you can clearly see one of them looks like a seesaw. And then if you have something like ClF3, where chlorine has 2 lone pairs of electrons, we did this Lewis structure earlier, so we have 2 lone pairs on the central atom, and we replace a second pair of electrons on the equator of the molecule. What's the shape left behind? It's a T shape. If you flip your iPad or whatever look like that, it does not look like a T. So it looks like a shape of a letter T. And so that's why we call that the T-shaped molecular geometry. And so if you look at the geometry and you can sketch it and can see it, you can make sense of the name. So you really don't have to necessarily memorize seesaw versus T-shape. If you can sketch and picture this geometry, hopefully you can see that it looks like a seesaw. If you can see and picture this geometry here, hopefully you can see that it looks like a shape of a letter T. So then if you have something like xenon F2, xenon will form compounds. These aren't stable enough to ship or to transport, but you can have xenon F2 form at really low temperatures compounds with fluorine. And so xenon has 8 electrons, 2 times 7 for the fluorines. So that's a total of 22 electrons. So we have a central xenon with fluorines on each side. And then that's 16 electrons. And the 6 leftover electrons are placed onto xenon. And so they're placed onto xenon around the central atom on the equator. And so at least you can see that the electron pairs are always going onto the equatorial positions when we're replacing the electron domain geometry of trigonal bipyramidal with electron pairs. And so then I mentioned before that if you have 3 total atoms, xenon F2 has 3 atoms, its shape is just named as either linear or bent. You can see it, that linear is the shape that would apply. Now if you think about the electron pair repulsions, you have the electron pairs trying to press one way, the other electron pair trying to press the other. The molecule is perfectly 180. So this molecule is perfectly 180 degrees in geometry. If you think of the geometries here, the ClF3 is a little less than 90 because the lone pair push the bond pairs into each other. The bond angles here are a little less than 90 degrees for SF4. If you look at PCl5, exactly 90. If you look at the equator positions, exactly 120, a little less than 120 for SF4. Let's think about polarity, because we've already thought about polarity a fair bit. 2 molecules on this page are nonpolar, 2 are polar. Which 2 do you think are nonpolar? Probably PCl5, because PF5 is nonpolar. So this molecule here is nonpolar. And then the xenon F2 is nonpolar. The polarity is all about the nuclei. Don't let the electron pairs confuse you too much. It's not about the charge that the electron pairs hold by the electrons being negative. It's about the charge that the nuclei end up adopting as their pull of electrons towards themselves. It's all about these bond polarities and what they are. So it's all about the partial negative charge in the 2 fluorines being exactly the same charge, and that those dipoles cancel each other out. So it's all about that charge of the F on the top is equal to the charge on the bottom, cancel each other out, so that molecule is perfectly nonpolar. And then the 2 molecules in the middle have electron pairs to not allow another atom to have the exact same charge opposing that charge on the opposite end of the molecule. So it's all about like this pair not allowing there to be an atom there to adopt the same charge. And so we lose the atom there, we allow sulfur to have a positive charge, the structure even changes geometry a little bit. Like for the octahedral, like I mentioned before, that all the positions are the same. It doesn't matter which of the positions you replace with an electron pair. So we take one electron pair away, you can take this position or that or this, they're all the same. So we replace one of the positions with an electron pair. Let's choose the bottom. We put our electron pair on the bottom for our 1 domain. Our 5 bonding domains, what name do you give that shape? It's a pyramid. It's a pyramid on a square, so we call it a square pyramid. So square pyramidal. And then if we replace another electron pair, it wouldn't make any sense to put 2 electron pairs next to each other. Probably make more sense to put the 2 electron pairs opposing each other. And so then the name we might give to a structure where we put the bonds opposing each other is square planar. So planar because all these atoms are in the exact same plane. So whenever I call a molecule something planar, it has to be totally planar for the atoms. We can have lone pairs sticking out of the plane, that's fine. We just can't have atoms sticking out of the plane. So we have 2 lone pairs sticking out of the plane. So planar molecule, nonpolar, SF6, nonpolar, and then we have a polar molecule in the case of BRF5, because we kind of break the trend of having an atom to oppose itself. I think the next slide is, no, that's not what I thought it was. This is what I wanted to kind of end on, is how SF4, how it changes its geometry a little bit. And this is because we have a lone pair here. So we don't show the lone pair in the molecular geometry picture because the lone pair isn't observed in experiments that show you the structure, but it's there, it's exerting its force, it's changing those bond angles from being perfectly trigonal pyramidal. So I think the key is that the structures are adopting the shapes we're showing you, and it's just a generalization for us to predict and understand those shapes, and the shapes are really close to those ones that we're predicting. In some cases, exactly. When we have exactly tetrahedral predicted for the geometry, that's exactly what we see experimentally. All right, guys, that's good for today. I'll see you back on Monday.